Welcome to today's CX seminar. It's my great honor to introduce Dr. Quan Nguyen. Quan is currently a postdoc at Princeton, and previously I believe he got his PhD from Washington University at St. Louis. And then Quan works on a lot of problems like active learning, Bayesian normalization, sequential decision making, especially for scientific discovery. So today he's going to talk about experimental design for data efficient scientific discovery. Welcome.
Thank you so much, Angie, and thanks everyone for being here. I know it's a pretty busy day for you all with the visit day and everything, so thanks again. Today I'm going to be talking a little bit about the research that I've done in my PhD, the research I've been doing in my postdoc, and a couple of future directions that I'm excited to look into. So to kind of motivate this problem, right? Want to start by saying that scientific discovery, and in particular drug discovery, is very expensive, very difficult to do. So you imagine yourself a scientist, right? You're trying to search over a very large database of molecules or drugs. So you want to find molecules with some good property of interest, like binding activity to a certain protein, so that you can synthesize those molecules into drugs that target certain diseases. So what you usually do is you want to search for these molecules in a sequential, iterative manner. So you start out picking out a couple of molecules from your database to perform experiments on. So these experiments can be, physical experiments that you perform in a lab, or some really heavy computation that you run with some computer program, so simulation, computational simulation. But what you want to do with these experiments is to want to inspect the molecules that you have selected, the properties of these molecules. So by inspecting the properties of these molecules, the experiments will tell you whether these molecules that you have selected have the properties that you're looking for or not. But what's crucial is that these experiments are very expensive to do. So if it's a physical experiment, right, someone will have to come in and they have to be very careful with the chemicals that they're working with. If it's a program that you run on a cluster, then it might take a lot of time and take a lot of compute that your advisor has to pay money for. So you want to be so the cost of performing an experiment is high. But after running these experiments, right, you will come back with labeled data that tells you whether these molecules that you have selected have the properties that you're looking for or not. And then you come back to the original database and pick molecules to perform experiments on. And the process repeats until you've run out of time or patience or money, right? So it's an iterative procedure in that way. And the question that the scientists need to ask themselves is which molecules to inspect at each iteration given the experiments that they have performed in order to best find what they're looking for. And to make this problem even more difficult, right, usually they have to deal with very, very big databases, very big search space of molecules. So an exhaustive search throughout every data point is literally impossible to do. So you need a more intelligent way to kind of search through these molecules. And what's interesting is that even though we've been talking about scientific discovery or drug discovery, this problem is this particular problem can be boiled down to a framework that is applicable to other applications too. For example, in hyperparameter tuning, where you're trying to find the best combination of hyperparameters for your model, like the architecture of your neural network, the learning rate. So you want to tune these hyperparameters to maximize the test accuracy, for example. But every time you try out a new combination, you have to retrain the model, and that might take some time or some GPU compute too. So you have to be very careful about which combination of hyperparameters to choose to experiment on. In product recommendation, right? You want to strategically pick out ads to present to a user of an e-commerce website to maximize some click-through rate, for example. But you don't want to present to them too many ads because that might disrupt their online shopping experience. So which data points to select, which hyperparameter combinations to try out, which add to present to the users. These are the questions that we have to concern ourselves with. But drug discovery is an interesting problem in and of itself because it's becoming more and more difficult. So in that domain, people have this term called E-Room's law to indicate this phenomenon that they have observed, where they saw that our capability of producing new drugs has been decreasing exponentially as a function of time. So this is like the reverse of Moore's law, which is what we've been thinking, what we've been used to, where it says that our computing capabilities have been increasing exponentially, right? So here is somewhat of a reverse where it's becoming harder and harder to make new drugs over time. So what a lot of people have been thinking about is, can we leverage the tools of machine learning, which we have seen so much potential in other domains, to help out with this drug discovery problem that is becoming more and more difficult. So in my research, I apply machine learning and specifically experimental design to tackle this problem, where experimental design is this framework of decision making, where you start out with some search space, and then search space of data points that you don't have labels for, but you train a predictive model that produce some predictions about the labels of those data points. And then this model guides what's called a decision-making policy to pick out new data points to label, new experiments to perform. And performing an experiment is modeled as querying an expensive oracle. So this oracle will return the label of the data points that you have selected. And then you update your data set and repeat this entire procedure until you run out of time or money. Oh, and I should say that please feel free to stop me anytime if you have any questions or comments. Now, what the goal in experimental design is, we just want to maximize some utility function of interest, and this utility function quantifies the goal of experimentation that you have. So it could be something as simple as searching for as many good data points as possible. So a good data point here can mean a molecule with binding activity to certain protein that we talked about, or it can be something like optimization. So you want to optimize for some characteristic that you care about. For example, finding the materials with the highest durability or ease of production, and some quantification of ease of production. Or it can be about learning. You have some phenomenon of interest that you want to learn about, so you search for data points that inform the most about the phenomenon of interest. Give data points that give you the most information about what you care about. So there can be different ways to design, different ways to quantify this utility function that tells you the goal of your experimentation. And the central question that we ask is, how can we design this decision-making policy at the top to help us select which data points to label in order to maximize our utility function?
You're using causal inference?
No, not using causal inference just yet. All right, so in my research, I've tackled these experimental design problems in different directions. So the first one in Bayesian optimization, which is a experimental design framework for optimization. So maximize some utility function of optimize for some objective function that works as your utility function. We study setting in Bayesian optimization, where you're working with a very high dimensional search space. And even though Bayesian optimization is a very label efficient framework for optimizing black box functions, which is what we care about, it works extremely well in low dimensional settings, where it tries to thoroughly exploring the search space to find the global maximizer. But as you can imagine, when your search space is very high dimensional, this thorough exploration of the space becomes more and more difficult. So in this work, we kind of sidestepped this problem a little bit and investigated a local optimization scheme that forgoes the goal of thorough exploration, but just learns about the gradient of the black box function that you're trying to optimize, and then proceeds with in the direction of the gradient of the function. So you can think of this as a Bayesian gradient descent algorithm that doesn't thoroughly explore the search space because it's impossible to do in high dimensions, but still does a pretty good job in optimizing the objective function that you care about. There's I've done a couple of works in what's called active search, which is the realization of this experimental design framework for the goal of searching for as many different good data points as possible. One example is in multi-fidelity active search, which is a setting that is relevant in a lot of different scientific discovery problems where you have multiple oracles of varying degrees of accuracy and cost. So you, when inspecting a characteristic or molecule, you can think of running a simulation on a computer as a low fidelity oracle that tells you some approximate answer to what you're looking for, and performing an actual experiment in the lab will be a high fidelity oracle. So how can you balance between these different oracles that you have access to maximize scientific discovery, which is the question that we care about in this book? There's another question, there's another relevant setting where instead of just finding as many good data points as possible, we care about finding a diverse set of data points. And this is very common in scientific discovery, where the domain scientists might not care about just simply optimizing for some function of interest, but they care about diversifying their knowledge so to improve their scientific understanding of a phenomenon. So in this work, we propose a new utility function that induces a diversity-aware search strategy that would return a diverse set of data points. And finally, in my recent book, I've been thinking about the goal of active learning. So instead of just maximizing with Bayesian optimization or searching for as many good data points as possible, now we care about active learning. So learning about some phenomenon of interest, not just collecting good data. So the goal here is want to gain as much information about some phenomenon of interest as possible. And this is the work that I've been doing in my postdoc, where we propose what's called a global active learning policy that allows us to reduce our uncertainty about some very high dimensional objects. So it requires a way to quantify our uncertainty in high dimensions. And in this talk, I'm excited to talk about the last two branches of this work in diversity-aware active search and active learning, and the connections between the two.
What's the definition for oracle here?
Oh, the oracle here is some mechanism that will return the label of a data point that you have requested.
Oh, okay.
So it can be like performing an experiment or running a heavy computer job, or even a human that you query to label the data. Okay. So let me start out with diversity-aware active search, which is a experimental design framework. In traditional active search, you work with a binary setting. Each data point is either good or bad. If it's a good data point, it's a target that you're looking for. It's very rare, but it's still there. If it's a bad data point, then you want to avoid that data point in your search. Now, in multi-class search, we assume that each data point belongs to one of the C classes, where class 1 is still the bad data points. Class 2 to class 3 are good data points that you want to look for. In traditional active search, where it works in the binary setting, the state-of-the-art policy might induce this oversampling behavior where it focuses on a region that has a lot of good data points. So it might over a region that contains a lot of good data points that it has discovered. But in a multi-class search case, oh yes, please.
So I want to make sure I understand the multi-class search problem. So you know all of the points X and you don't have any of the labels Y and you can query for them?
Yes.
Okay, thanks. And there's some metric on the space.
Yes, there's some way to describe the features of the data
Yep.
points.
It's fully featured. It's not just a metric.
Yes, thank you. Okay, but imagine in the multi-class case where you're working with multiple classes of good data points of targets, then you might say that, oh, not all discoveries are created equal, right? Some discoveries are more interesting than others. In fact, a novel hit in an unexplored region might be worth more than making yet another discovery in a known region. So this motivates a utility function that has diminishing returns in making additional discoveries, right? Where the marginal value of making another discovery should decrease with the size of the class, the size of the target class that you have discovered so far. So one example is this log function that increases but kind of tapers off as the input increases. So we introduce this new utility function that is different from the binary setting, which simply counts the number of positives that you found. This utility function includes a positive increasing and crucially concave function for the number of targets that you found for each target class. So it will encourage diversity in the targets that you have found. Now, the question is, how can we come up with a decision-making policy, an active search policy that design queries to maximize this utility function of interest? One particular tool that is very attractive, especially if you worked with Bayesian decision theory before, is this Bayesian optimal policy that picks out the query that maximizes the expected value of your utility function at the end of the search. So it cares about maximizing the average value of the utility function that you get after making all the queries. So this might sound simple, but as you can imagine, this involves a very expensive search. So you have to iterate over all possible situations that might happen in the future. So you have to reason about the effect of all future decisions that you make, not just at this current iteration, but all future iterations until the end of the search. So this incurs an exponential cost increase.
Can you prove that it can't be done faster?
Well, the idea is there's no way for you to compute this optimal action until you have kind of iterate through.
No, I understand the worst case, but like in the secretary problem, you can exploit structure of the problem. So I believe you when you say you can't do it in this case. I'm just curious whether you actually have a proof that there is no shortcut. Like it's an NP hard.
I guess it is. It is NP hard, and even though we didn't look into proving that this, there's no way to shortcut this, but we did look into a different negative result, where we proved that any polynomial time policy can do won't be able to approximate the optimal strategy in by any constant.
Oh, okay. So you found it's inapproximable. Okay. Yeah. Good enough for me. Thanks.
It's not quite the same difficult hardness result that you were asking for, but I guess it's a different kind of hardness result.
Okay, I'll ask later.
Okay. Okay. So this exhaustive search is very expensive, and it's very expensive to do, especially in with long decision-making horizons. Unless your decision-making horizon is very short, like 1 or 2, especially if you only have one decision making left, then it's very easy to compute the Bayesian optimal policies. You just look one look ahead into the future. So in order to deal with this exponential blow up in computation, a lot of active learning policies come up with this greedy myopic heuristic where they assume that indeed the decision-making horizon is very short, so they ignore the rest of the horizon, assuming that we only have one decision to make left, and they compute the optimal action to make, assuming that you only have one step to take. So this gives you a very efficient policy. You only need to look one step into the future, but it's myopic in a sense that it doesn't account for future decisions that you can make. So it might misjudge some of the actions that you can take there. So in my research, I care about finding ways to kind of move away from this myopic heuristic and still try to account for the entire decision-making policy that we have left. One particular heuristic that we have used is this batch rollout heuristic. And the idea of this heuristic is that instead of iterating over the remaining decision-making horizon, one step at a time, we assume that all future steps are taken simultaneously in one go. So all future decisions are made at the same time. This means that all future decisions, all future layers in your search tree are concatenated into one big layer. So after this current iteration, all future decisions are made simultaneously in a batch of queries. This means that we can still actively account for all future decisions that we can make, but ideally, we won't have to incur this exponential blow up that we saw with the exhaustive search. Now we only have to deal with two layers of search in our search tree. So by making this simplifying assumption, we can try to avoid that exponential blow up while still accounting for how many queries we have remaining. So with this batch rollout heuristic in hand, we can realize what's called a non-myopic search policy. So let me show you the effect of the policy that we just designed. First, by comparing against the behavior of the binary active search setting, where we saw that it might oversample a region with a lot of good data points that it has discovered, where a diversity-aware active search policy that we just designed will be able to more equally distribute its queries across the different classes, which is exactly what we wanted to do with our utility function with diminishing returns. And we've been looking at this type problem, but this behavior generalizes to more real-world applications like drug discovery too. Now let me talk a little bit about the non-myopia that we induce in our decision-making policy. And in order to do that, I'm showing here this plot that is a function of time, so a function of number of data points that you have collected. And here I'm showing, not yet, but the y-axis will be the difference in the cumulative utility between our policy, which is non-myopic, and the one-step policy, the greedy myopic policy. So because it's a difference between utility, anything that is above zero means that we are doing better than the myopic one-step policy. If it's below zero, then we're doing worse. So the trend goes something like this, and it's quite interesting. In the beginning, we actually do worse than the myopic policy. So by being non-myopic, you're doing worse in the beginning. But then as time progresses, right, as we find more and more data points, we do better. So we outperform the myopic policy. So this trend actually illustrates something interesting in decision making, where in the beginning, our policy, which is non-myopic, spend some initial queries exploring the search space because it knows that there's still a lot of decisions left to make, a lot of experimental budget left. So it can afford some initial budget exploring the search space, finding out about the search space more. But as time goes on, it will smoothly transition to a more exploitative behavior and ultimately outperforms the one-step policy. And this exploitation trade-off that is crucial in any decision-making task is automatically achieved with this non-myopia thing that we worked into a policy. Yes.
Okay, so you need to know how to select the batch at the second step, which is not a rollout, but it's a much bigger decision. And it seems like there are two ways to do that. One is that you could model your own policy and say what kinds of batches do actual rollouts give you, and you have some approximation to that.
Yeah.
Like by DPP or something. And the other possibility is that you can actually optimize, find the optimal batch thing, which is what I suspect you do.
Yes,
Yeah.
we do care about that. Let me try to see if I actually have it as a skip slide. So, okay.
Yeah.
So imagine yourself in the binary setting, which is slightly simpler. Oh, and by the way, for everyone, we are talking about this step of when you're trying to decide which data point to select at the very first step, you need a way to quickly compute this batch of future decisions. So imagine yourself back in the binary setting where everything is just the label is just 1 or 0, then it's quite easy to compute. It's quite easy to compute this batch because you just pick out the top K data points. So that's not quite hard. In this multi-class setting, it's slightly
Yeah, okay, you've got FC is concave.
yeah. So you're able to approximate it using Jensen inequality. Okay. Yes, please.
Do you have a sense, an intuition of what's a hard instance in which the competitive ratio between like the greedy and the optimal is the worst? And does this do better in that case?
So you're asking about the difference between the greedy policy and the non-myopic policy, or the
optimal.
the optimal
Yeah.
policy?
Just compared to the optimal, do you have an intuition of what's the case in which the optimal does much better than either the greedy or your
Thanks so much for the question. So let me tell you a bit about the hardness result that Jason and I were talking about, where it said that any polynomial time policy, which non-myopic policy is one of them, cannot approximate the optimal policy by any constant. And it's proved by construction. So we came up with these very crazy active search problems that it's literally impossible to kind of decode it unless you spend an enormous amount of time to do it. So in that way, it's problems where there is so much structure in the future space that you have to think very carefully about what's going on. Now, in my own experience, the difference between the myopic and the non-myopic policy becomes very large when you have different clusters of targets in your space. So you can imagine the greedy algorithm just focuses on one particular cluster. It doesn't explore, so it just stays within one cluster, which is quite bad if you have a lot of clusters. But if your search space does indeed only have one cluster, then there might not be any significant difference. In fact, the non-myopic policy might do worse, but it's not. It doesn't do that much worse than the myopic policy does worse than the non-myopic when there are clusters.
Thank you.
Thank you.
Sorry, can I ask one more question here? I mean, if you're behind time, I won't.
Are we doing that time? I don't think so.
I think I'll okay.
Yeah.
Yeah. So the batch approximation seems like a good idea in general. Have you looked at it in other settings beyond the multi-class active search problem?
Thanks for the question.
Like I'm thinking about how I'd work this out for guessing processes. Yes.
Yeah, so imagine in the Bayesian optimization setting with a Gaussian process, people have indeed investigated this too.
Yep.
The the problem is how, like you said, how to quickly construct this batch of future queries.
Right,
So one thing
exactly.
that they've done is to artificially introduce diversity within that batch of queries too. So they might say that, oh, my future decisions, they focus on promising data points, but they should be like well spread out across the space. So they do expected improvement, and then they put a DPP in there.
Yes, this is okay, but this is not exact, I'm guessing.
It's not exact.
Yeah. Also, you can't maximize the DPP, but
Well, you can maximize the likelihood, right? So
I don't think you can do map inference for DPP. You can only sample. I think it's intractable to actually find the most probable sample.
I think that is essential. Yeah. So they treat expected improvement as like the quality score, and then they put DDP in there as like the diversity. So balancing each out.
Yeah, thank you.
Right. Okay. To conclude this idea of diversity-aware active search, I'd like to quickly talk about a side note on like a follow-up work. So we talked about multi-class active search, where we want to encourage diversity in the labels of the data points that we've collected. So this setting is relevant in scenarios where you indeed want to induce diversity in the label. So one example is where you're searching for molecules that can bind to multiple target proteins, and you want to target many different proteins. So you want diversity in the behavior of binding in that way. But there are settings where you don't actually have a multiple classes. You indeed still work within the binary setting, but diversity is still something that you care about. So is there a way to encourage diversity in the features? So you still want to find many different targets, but now the targets should be diverse in their features, so that you either don't have to commit to one particular solution while you produce these molecules into drugs, or you improve your understanding of the problem that you're going for. Now, what you want to do in this case, what you want to encourage diversity in the features, is you want to come up with a utility function that expresses this idea as well, just like how we came up with the diminishing returns idea for our utility function earlier. So one idea in this case is to use some sort of an effective count as your utility function, where this effective count will return a low number if the data points that you found are very similar to each other in the feature space. Or this effective count will return a high number if the data points are very different from one another. So you want to find a way to account for the similarity of the different data points, similarity in the feature space. So one idea is this particular function called the Vendi score, which has its roots in ecology. Its form is something like this. It's the exponential of the Shannon entropy of these lambda values, where these lambdas are the normalized eigenvalues of the covariance matrix of the targets in your data set. So it's quite a mouthful, but the idea here is you take the data points that you found, you compute the covariance matrix of those data points, decompose that matrix to get the eigenvalues, and then you look at the Shannon entropy of the probability distribution defined by those eigenvalues. So you look at how varied those eigenvalues are, and that will give you an effective count measure for your data set. And let's look at a couple of examples on the right here, where we saw that this effective count function is able to actively account for the similarities between the different data points. So if your data set in this first example has a lot of duplicates, then the effective count utility function will treat it as the same data point. So it only return 3 data points in this case because there are effectively only 3 data points. But if there are more going, if there's more going on in your data set, if your data points are slightly different from one another, then that effective count number will appropriately increase. And we are able to induce this, we're able to account for this computation because we are computing this covariance matrix that we're showing here, which actively accounts for the similarities between the different data points. And by using this effective count as a utility function, we can apply it to various active search and Bayesian optimization problems in order to find many diverse data points. So here's one example from a materials discovery problem that I worked on, where we try to find both metallic classes that have high durability, but we still care about finding diverse classes. This is one example from path finding, where we want to find most efficient route from point A to point B, so 2 corners. But because there might be some obstacles along the way that we don't know about while planning, so we want to find many diverse routes that get us from point A to point B, so that we can have like a backup strategy when we actually execute this task. But so by using this effective count function as a utility function, we're able to actively account for the similarity in the features of our data points. All right, I have here a blank slide.
Critical question. So
Yes, please.
it seems to me like you're trying to do the diversity, but then in a lot of like standard discovery, you also have other utilities, like whether this is used for protein design or something like that, right? So are we trying to say here with 2 steps? You first do diversity and then you pick one of them. That's kind of that's trying to optimize some other like utility. And how do you compare that to some maybe strategy that try to have both diversity and the utility is the objective function and then directly do the optimization?
So what we're doing here is actually the second approach that
Oh.
you described, where the utility function only takes in the good data points that you found, and then calculates the diversity of the good data points. So the data points have to be good already,
I see.
and then we care
The
about.
amount of the ones that you want diverse one. I see.
Yes, please.
Is any sort of relationship to DPPs, like the probability under the DPP be proportional to the determinant, which is like the product of the eigenvalues? So this is maybe like a smooth version of that.
That's very insightful, and you can imagine it as having similar behavior, where a data set that maximizes this one will also maximize the diversity quantification by the DPP2, where you imagine if all samples are completely dissimilar. Let me try to go back here. If all samples are completely dissimilar, then your covariance matrix will be just the identity matrix. And then all these eigenvalues will be 1/n. And that will maximize this like Shannon entropy function, because it's like maximal entropy, maximal diversity. And when you have a covariance, the identity covariance matrix with a DPP, you also have a highest diversity in that case too. Now, just because the maximizer of this function is the same maximizer for that function doesn't mean the 2 functions behave similarly, right? And the edge case is when you have duplicates. Then if you have duplicates, then the
DPP goes to
value
0.
will be 0. Well, here it will be something else. And one motivation for this effective count function that we talked in the paper is that sometimes we just don't want to have 0 as a utility function, because it kind of ignores all the progress that you have made already. So this is like this effective count function with the Vendi score thing. It avoids that edge case a little bit. All right, so let me try to move on to the second part of my talk, which is on active learning. So instead of active search, where you're just trying to find good data points, here we want to find strategic data points whose labels will tell you a lot about whatever you're trying to learn. So you have some phenomenon of interest that you care about, and you want to gain as much information about that as possible. And here I'm using an image classification problem in ecology to motivate this setting, where imagine you are an ecologist and you care about monitoring the diversity of the animals within some region. So you set up what's called these camera traps around the region that you are interested in, and these camera traps will automatically take pictures whenever there's movement within the area. So you have a huge amount of data in the form of pictures automatically taken, but these data are unlabeled as well. So in order to gain information about how diverse the animals are within this region, you have to ask experts to look at these pictures to label which species are present in your pictures, and from that information you'll be able to approximate the biodiversity of the animal population. Now the experimental design problem is still the same, right? Every time you ask an expert to label one picture, it might take them a lot of time and a lot of effort, and then you have to pay them as well. So you want to minimize the number of times that you ask an expert to label your pictures. So you want to strategically find informative pictures to gain the most information about all the images that are already taken in your database. So the goal here, want to be more precise, is to find data points across the entire database to minimize our joint predictive uncertainty about all the labels across the database. So if we call theta the very long vector of all the labels of the data points in a set, then what we want to do is we want to place a distribution over theta, and then we want to select data points that will help us reduce our uncertainty in theta. So reduce the spread of this distribution of this theta vector. Now, a couple of problems that you might run into. Theta here is very, very high dimensional. So the size of it is just the number of images that you have in your database. Can be in the number of millions or even billions. And if you want to minimize your uncertainty about theta, then you have to have a way to quantify that uncertainty in the distribution of theta. But traditional uncertainty measures like variance or Shannon variance, first of all, doesn't really do a good job in quantifying uncertainty. Shannon entropy might run into a lot of problems where you're working with very high dimensional spaces. So most active learning policies instead focus on what's called local uncertainty, where we just look at individual predictions and then say, oh, I'm very uncertain about this particular prediction. So let me label the data point that corresponds to this prediction, and that will work as reducing my local uncertainty. So we just treat individual predictions as measurement of uncertainty.
So I might be confused about it looks to me like the blue and the red are playing different roles. So I thought red, you were talking about the heuristic, the acquisition heuristic, whereas blue, you were talking about the goal that you hope that heuristic will serve. Oh,
yeah.
okay.
Thank you. Yes. So yes, imagine that we really want to do this, but doing this is quite difficult. So let's work with this heuristic instead. But with this heuristic, right, you might run into this problem where one particular data point you might have a lot of predictive uncertainty about, but as you label it, that data point might not inform about other data points in your data. So there's still that mismatch between local and global uncertainty in that way. So can we do better? So this comes down to the ability to quantify uncertainty in high dimensions, right? Which is a very, very very difficult task. Now, our idea is to look into diversity again. So imagine that we spent some time earlier looking at this effective count function, which quantifies the diversity of the data points in a set. But in our work, we noticed that diversity can be considered a quantification of uncertainty too, where if you have a lot of uncertainty in a random variable, so the distribution of that variable is well spread out, then when you sample from that distribution, the samples will be quite diverse. If you have very low uncertainty about some random variable, then the distribution will be well concentrated. So the samples that you draw are very similar to one another. So diversity seems like a good way to quantify uncertainty that is sample-based. So you just need to draw samples from the probability distribution, and you can use that to quantify your uncertainty about the random variable that you're working with.
Yeah, so I guess I worry about whether I believe your features. Like, what if I throw in lots of random irrelevant features? And so the covariance matrix ends up becoming close to, close to random.
Yeah, so that is a requirement that you kind of have, right? You have to have a good you have a good way to measure how similar data points are to one another.
Yeah. But you would want that to actually take into account your downstream utility. Of being able to get labels. Like instead of taking the features you're given, shouldn't you be learning how to weight the features or how to transform the features nonlinearly in order for this to actually give you things that help you predict other points? Like I'm wondering about this method versus gradient alignment methods, where you say, if I learn on this sample, how much information does it give me about the other things?
So you're making a comparison between the two methods and how they.
Yeah, I'm saying you're not looking at the downstream utility. You're just saying if things are close together, they're redundant. And if they're far apart, then they're not redundant. But if I throw in a lot of random features, then they could be pretty much orthogonal, but still not redundant because the orthogonality comes from the random features.
Sure. So in that way, the way that you're comparing the similarity between the two data points might not be reliable, you're saying?
Well, I'm saying that there are ways to make it more reliable by looking at downstream effect of learning on the data points that you're acquiring.
I see what you're saying. And I agree. And so for example, in I guess I'm coming back to the Bayesian optimization example.
Right.
Again, if we're using a Gaussian process and you just use that kernel as your to compute the covariance matrix.
Right. So you should interpret my question about why do you take a given kernel in the Gaussian process instead of learning the kernel?
So
I know it's hard to learn kernels, but there's a lot of people using neural nets, and so we use learned features all the time. Yeah.
But with a neural net, you have a way to do that too. So with a neural net, as we will see, you have embeddings and you can compute the cosine similarity. So you are in effect using the cosine kernel as your kernel to compute that covariance matrix, and that will take into account.
Okay, it sounds like you're about to talk about this, so I'll shut up.
But do stop me if later I'm not answering your question in a satisfactory. Anyway, okay, let's try to pursue this idea of using diversity to quantify our uncertainty in high dimensions. So by using this particular function that just takes as input a data set of samples that you draw from a probability distribution, it doesn't actually make any assumption about the underlying distribution at all, which is a plus when you compare it against other uncertainty quantification methods where in order to quantify uncertainty is assuming that there's some underlying distribution. And further, it just, again, works with samples. You just have to be able to draw samples from your predictive model, and you'll be able to quantify your uncertainty in your predictive distribution that way. And we looked into the theory of this function a little bit, and we also realized that it's a generalization of Shannon entropy, which is a very common way to measure uncertainty, that accounts for similarity. So Shannon entropy just cares about the densities of the different realizations in your probability distribution. But here we also care about similarity, which seems like an important factor when you think about uncertainty too. Okay, so let me talk a little bit about the active learning policy that we realized using this diversity metric as our uncertainty quantification. So so remember the requirement that we just need to be able to draw samples from the probability distribution we're working with. So in this image classification problem, we use a dropout neural network where you might know that a dropout neural network is an approximation of a Bayesian neural network that is trained with variational inference. So if you enable dropout when you're making inference, then you'll be able to draw samples from the posterior distribution. So you perform a lot of forward passes with dropout enabled, and you'll be able to draw samples from that probabilistic neural network. So with those samples, you have a way to quantify your uncertainty in the labels across the entire data set. And then you can pick out data points that will allow you to decrease the most your uncertainty in that data set, where uncertainty is again quantified by diversity. So in this way, we have a way to realize what we call a global active learning policy that selects images that will help you inform about other images within the data set too. So here now, you're not just limiting yourself to local uncertainty, but you are picking images that will inform about the labels of other images. And we realize that thankfully, this global active learning policy is able to lead to better active learning performance in sense of classification accuracy with lower number of labeled data points, which is very nice to see. And interestingly, we found that one particular behavior that sets it apart from other policy, even though it might be a little bit difficult to see here, is that this policy, VIG, color in red, collects more diverse data points, so more diverse images than other policy. And that might be a side effect of using diversity as our quantification, uncertainty quantification. Anyway, to kind of wrap up this idea, I also like to point out that uncertainty quantification in high dimensions have a very wide-ranging set of applications, not just in active learning for image classification, but in other tasks as well. So in an experimental design task called level set estimation, where you want to learn whether each label, you are in a regression setting, by the way, where you want to learn whether each label exceeds a certain threshold or not. So here, the random variable theta that you want to gain information about is this very big binary vector that indicates whether each label exceeds a certain threshold or not. And this level set estimation has a lot of applications in environmental monitoring, where you want to see, oh, I'm looking at this very huge lake, and I want to find regions where the toxicity level exceeds some human safety threshold.
I'm sorry, when you say the label exceeds the threshold, do you mean the measure of that label?
The value of that label. So this is a regression setting now where the label.
Oh, I'm sorry, I misunderstood. Okay, when you talked about the region of the lake, I thought you were interested in the integral over.
No, just the different data.
Yeah.
Thank
you were trying to find individual data points.
Individual data points.
Okay.
Although
it seems like there's a lot of coordinates in that lake, maybe uncountably many.
Exactly. So the integral thing opens up a different active learning problem that that I'm not prepared to tackle just yet. Okay, so we found that by using this diversity based uncertainty quantification method, we're able to realize an a level set estimation active learning policy that is able to outperform the baselines within the level set estimation literature as well. So there is a lot of potential for using this kind of information gain approach that in other active learning tasks that has not been possible before, because again, the task of quantifying uncertainty in a very big high dimensional vector is very difficult to do. Okay, so to quickly wrap up my talk, I'd like to kind of briefly talk about another side of my research that I also enjoy, which is applying these experimental design tools to the different domain sciences. We've talked about how there is a lot of potential for machine learning to accelerate the different tasks in different fields. And I've been fortunate enough to be able to collaborate with domain scientists like chemists or material scientists on their own problem. So I'd like to talk a little bit about some of them. So in one particular application, we care about discovering photo switches, which are these particular molecules that react to light in a certain way that can be synthesized into performing very important applications. So by using the active learning policy, active search policy that we talked about, where we care about finding as many good photo switches as possible, we're able to find almost 3 times more photo switches than a random search baseline, which is what a domain scientist would be using without machine learning. In another collaboration with visualization experts, we care about developing a UI where a human is exploring a search space of data points aided by some active learning policy. And in this particular study, we use the use case of an intelligence analyst looking through a big database of tweets, finding tweets about a phenomenon that they are interested in. So they're foraging for information within data generated on some social media. So some social media website. So we're able to see that by being aided by machine learning on this particular active search, media explorer is able to find more relevant data points than someone who's not aided by machine learning. For the last one, recently we worked with some domain scientists to optimize for the properties of organic frameworks, or MOFs, which are these very interesting materials that can absorb toxins in the air and keep them inside their molecular structures. So as you can imagine, this has a lot of application in environmental settings. So we care about maximizing the ability to absorb and storage of these toxins by this MOF materials. And we were able to find that by applying Bayesian optimization, we were able to not only outperform random search, which is the baseline, but also find theoretical MOFs that outperform the state of the art in the MOF literature, which is quite nice to see. So overall, and now I'd like to talk a little bit about some future directions before wrapping up this talk. We talked a little bit about that uncertainty quantification method using diversity, where it just works on samples. And because it works on samples, we can look into different ways to improve the approximation of this metric by studying the behavior of the error bounds or reducing the variance of this metric. And we can also explore its applications in other active learning tasks too. Again, quantifying information in high dimensions is a very common problem. So there is a lot of work to do in this space. And finally, I've also been thinking a lot about how to work to improve upon the non-myopic idea that we talk about, non-myopic search idea. One thing that Jason has hinted at is that, we can try to do this using Bayesian decision theory or whatever. Or can we do even better by learning how to come up with a non-myopic search strategy, for example, via reinforcement learning? So one particular idea is that is to leverage the tools that train large language models that we've seen to be really good, right? Where we saw that LLMs are really good at optimizing for sequences of tokens. So there's potential for leveraging this technology to learn to optimize for sequences of experiments, sequences of labels that you query in order to best optimize your utility function. So you kind of create a large language active learner in that way. All right, to finally wrap up my talk, I realized I'm a little bit out of time for. In my research, I care about tackling data efficient learning, where the cost of performing an experiment is very high. So we need to be as efficient about the labels that we collect as possible. My approach is we want to use principle-based decision-making that is either based on Bayesian decision theory that will induce non-myopic planning, or some information theory that will help us identify the most informative data points as possible. And the overarching goal is to develop practical experimental design tools that will aid scientific discovery. And I'll be very interested in exploring collaborations for experimental design, also uncertainty quantification in high dimensions, which has a lot of applications in different fields, and other domain applications in the hard sciences, but also social sciences and humanities that can benefit from this data efficient learning as well. Thank you so much for being here at my talk, and I hope you enjoy the rest of your day with the PhD visit.
For a few questions. I'll start with one. So in active learning, you kind of need to use the kind of unlabeled pool, right? So, and then can you talk about like the efficiency of that, and then what if you want to extend to cases when you do not have a finite number of like the pool, unlabeled pool you, for example, in LLM, you want to do active learning, and then this possible sequence is like huge.
Yeah, that's a very good question. I haven't been able to look into any theoretical guarantee in terms of approximating the quality of the solution that you have if you have unlimited access.
Yeah.
There is a slightly related problem where people have tried to use LLMs to not work within one particular search space, but be able to generate new data points, new suggestions that didn't exist before when we started the problem. People have found that the data points the theoretical data points have been quite good, but some of them didn't look realistic. Like when you're working materials discovery or whatever, a domain scientist might look at it and say, "Oh, I don't know anything about this material. It doesn't look like anything that I know." So there is a lot of I guess trust issues.
Yeah, or feasibility, like
feasibility.
Yeah.
Yeah.
Because
So
in material science, like it can be a case that
Mhm.
you get diversity, but then it's actually not something feasible to them.
Yeah, I don't know whether that's a good thing or bad thing, actually. It might be a good thing where the LLM has free reign into suggesting whatever data point that it has, and then we'll improve our knowledge. Maybe it does. We have to account for it somehow. If producing it, working with it might incur some safety costs.
Yeah, so some constrained version of
Some
that.
constraint.
Yeah. Any?
Back to the plot where you show the cumulative gain over the myopic approach.
Yeah, I'd love to. It's one of my favorite plots.
Okay, yeah, we spent a lot of time on it already. So.
This one.
Yeah, and I was just wondering what kind of happens. It seems like there's some sort of phase transition there where it's like it's monotonically going up, and then it kind of
Oh yeah.
stops. And I was surprised that Yeah, does that mean that the myopic approach is actually now gaining upon the non-myopic approach a bit? And that was surprising to me because I thought the non-myopic approach would, or the myopic approach would like kind of, saturate very early. And then
Excellent question. And so I guess I should say first that this plot is like an average across all problems in the paper that all experiments, all data sets that we use in the paper. So the trend that you see here, it comes from a couple of problems where the non-myopic approach doesn't do well against the myopic approach. In other cases, you're right, where the trend is at first it goes down and then goes up completely. But in some other cases, it keeps going down. And this actually speaks to an interesting problem that you encounter with non-myopic planning, where you rely on your predictive model to help plan your future decisions, but your model is wrong. In particular, in this particular paper, we use a very simple k-nearest neighbors as a model, and in those problems where the non-myopic approach doesn't do well is when the k-nearest neighbor is not an appropriate model for the data points that you're working with. So it illustrates the importance of using a good predictive model for your experimental design.
would there be a way to detect that online and kind of switch to maybe the safer myopic approach?
It would have been nice, and yes, being able to detect it online would be the best case scenario. The thing that we've been doing is just to have a human monitor the process in real world experimental design and just keep an eye for what could be going on.
Thanks.
Thank you.
I have another question. It's kind of fundamental. So you're using Bayesian optimization as kind of like a sampling strategy as opposed to a modeling inference strategy, right?
That's right.
So at what point do you reduce the feature set? I didn't see that. Or maybe I misunderstood something.
Could you talk more about?
You're doing feature reductions with Bayesian optimization as well, right? Or no?
No.
Okay.
If you were referring to one of the first slides where we talked about Bayesian optimization in very high dimensions, then it's just about learning the gradient of the objective function that you're trying to optimize and then follow the direction of that gradient.
Okay.
Thank you.
If there's no more questions, let's next speaker again.
Thank you.
You actually do the offline version, which is like this real thing, and you model pick some points and then to see that what labels from the real sky.
Yeah, we did it online, which was very risky, I know. But
So how long does it take for them to give you?
one round was about one round was like
I see. So it's like you pick 20 points and they will spend a week on that and give you, and then you do another round.
Yeah.
And then another 20. Wow.
and they kept asking me, oh, where can we stop? I was like, I don't know.
But did you find the new points interesting?
Yeah.
Okay.
Yeah, so I would not have been able to tell myself, but they told me that, oh yeah, we found a couple of ones that that were interesting, and these domain papers that usually follows that we describe our experimental design framework and then shows those optimization thoughts, and then the second part of the paper they'll actually go into those interesting data points that they prepared and then show a couple of thoughts.
That's good. That's good.
Oh yeah, these data points.
Because I also have the worry that like what we design as the objective function maybe does not really quote unquote work for experts or scientists. Like, oh, it's optimized for this, but I do not find that they're useful in their own discovery process. So
I know I don't know if you come across this in your work, but there's this paper called Genome from DeepMind that a lot of people cited that did materials discovery, and there were some criticism about how it didn't actually propose any interesting ones, which is like, and there are parts that we kind of know about already. which is
Okay.
like simple variations of those points.
Wait, like even though they evaluate like the good utility in their
Yeah,
experiment,
really good.
but then it's actually not good for the.
Not like novel.
Novel.
Yeah, so novelty is what they.
Yes, then how, but yeah, that means you need to find different metrics for novelty.
Oh, yeah.
Hmm. Yeah.
Hey,
Eric, nice to meet you.
Nice to meet you,
Yeah,
Quan.
yeah, we're going to lunch. I think we're waiting
Oh,
for Jess.
Yes, yeah.
I don't know
nice.
if she's here. I guess we can wait.
What can I wait? I think
So-
still, yeah.
Close enough to walk there?
Yeah, I think you can walk for the restaurant tonight. You probably need to take a
Okay.
lift. Yeah, but it's also not that far. Maybe 10 minutes
Hmm.
drive
Okay.
close
okay.
to the campus.
Yeah, I took the Amtrak here and it's very close to where I'm staying. to, The study. It's like 7 minutes drive.
Where are you going for dinner?
Dinner is the Cosima. Do you know Cosima? Like the in one of the meal.
Oh, okay, over there. Yeah. Okay.
It's go that direction.
Yeah. Okay. It's near the Spanish restaurant we've gone to before. Did that like?
Yeah, they
Burn
had
down
a
or something?
fire.
Yeah.
And then
oh,
it's closed. I want to reserve that
Yeah,
one. Then
yeah,
Tony
that was
said
so
they
good.
recently got a fire and then it's closed.
Okay.
that was Kuchara. Yeah.
I wonder what happened.
It
Yeah.
means the spoon in the
Okay.
Spanish.
Yeah.
Mm.
Okay. So yeah, that was when you said Cosima, I was first thinking of that restaurant. I was like, wait, didn't that burn down? But no.
Right. So I cannot book
Same
that one. So I have
yeah.
to book the other
Yeah.
one. Yeah. Cosima is an Italian
Okay.
kind of restaurant.
During my PhD, there was a restaurant that burned down in St. Louis too. But that restaurant, the first floor was the restaurant, but then the second and third floors were apartments. And one of my friends was staying in
Oh, really?
one of the
Wow.
apartments. Yeah, so he had
The
to.
fire comes from the restaurant, like they.
Yeah, so
Oh,
someone left an oven on or something.
Oh,
okay.
Was anyone injured or?
No, thankfully no. Yeah.
Yeah, we'll see. I hope they reopen and then because that's one of my favorite. The
Is it good?
Spanish one,
Okay.
the one's my favorite.
It's
We need to check that.